Hello and welcome. In this video, we're going to take a look at one of the reasons why calculus was invented. We're going to take a look at a problem that seems pretty straightforward to explain. It's easy to visualize, but computationally difficult until we start inventing this whole other branch of mathematics. Well, let's take a look at a visualization of this problem. So here I've got a function y equals f of x in blue. And the goal here, the tangent slope problem, says what I'd like to do is take a line that goes through this red point. Here I've got that labeled as a comma f of a. And I want to find the slope of a line going through that point where the line is tangent. And that would imply that this line here does not cross the blue graph in the little neighborhood around a. If I were to extend this line eventually, yes, it would cross the function, but it's tangent because it's not crossing nearby that point. The goal here is to find the slope of this. Now, if I've drawn this function just perfectly, and I also have grid paper, and everything is to scale, then maybe I could actually use the grid paper here to kind of estimate this slope. And, according to my estimation here, it seems like it's definitely not quite as steep as -1, but it's definitely negative. That's not really quite good enough. We need a better way to be able to figure out what the slope of this is computationally. And one of the ways that we would compute slope is by just the definition, rise over run. Now, rise would be given by subtracting the y coordinates of 2 points, and the run would be subtracting the x coordinates of 2 points. But I only have a single point here. So this particular point here, maybe that would be my x1 and my my y1. I could plug that into the formula, but I need a second point. And I don't have another point this goes through. That's the whole idea of the tangent line, is I just wanted to go through this one point. I don't know any other points on there. So we start doing a little bit of a conceptual idea here of approximating that tangent slope by choosing a second point. Let's see what I mean by that. All right, well, here is a second copy of that graph. And I'm going to pick a second point that's somewhere else on the curve. Why don't I pick a place over here? And I'll let this be b. And it has a y coordinate of f of b. So the coordinates of that point would be b comma f of b. Now I can compute the slope of a line going through those 2 points by using the same formula, where m is equal to the difference in y coordinates, f of b minus f of a, divided by the difference in the x coordinates, b minus a. And now that's not going to get me the same slope as that green line. What it's actually going to get is it's going to give me the slope of a line going through these 2 points here. So let's make that a black line going through those 2 points. All right, that's definitely not a tangent line. What we call that is a secant line. And a secant line goes through 2 points on the graph. Now, if you stop and think about it, the graph of the black line, the graph of the green line, they're pretty close. But pretty close isn't close enough mathematically. We need to do something better than that. Now let's start giving these points some names. I'm going to call this first point P, where actually I want the tangent line, and I'm going to call this second point, let's say, Q. Now, how am I going to get a better approximation? Q was just arbitrarily chosen at some distance away from P, but I can do a lot better if I choose Q to be a little bit closer. So I'm going to take this and call this point Q1, and I'm going to pick a new point that's a little bit closer, and I'm going to call this Q2. And then I can recalculate the slope of a line going through those 2 points. And that gets me a slope of another line. This time again, it's a secant line, not a tangent line. But if you notice, the slope of that black line is starting to actually look pretty close to the slope of the green line. So what we're going to be doing here is trying to calculate the slope as Q gets closer to P. As a notation, when we say something gets closer to something else, we tend to use an arrow mathematically. So this would now be as Q approaches P, then the slope of the secant line. As Q approaches P, the secant slope approaches the tangent slope. So this formula here, FB minus FA over B minus A, Rather than maybe just calling that m, we may want to denote that with m with the word secant, or just SEC for short as a little subscript. That is the slope of the secant. Now, as we approach P, as Q gets closer and closer to P, then we start getting a better approximation. Now there's a different way we might want to phrase that. Rather than just calling these points A and B, why don't we actually specify the distance from A to B as being some real number, where this distance, let's say, is h. Now, in the case where we may have chosen Q as a point to the left of P, h can be positive or negative. So it's not so much distance so much as it is we take A and we can add a value h and get B. If h is negative, that will give us B less than A. So let's rewrite this graph, but instead of using B, let's actually give that in terms of A and h. So one last time here, same graph, but instead of using B, that value can be represented as A plus some real number. And again, if h is negative, A plus h will just end up showing up farther to the left on the real number line, and we can actually get a point back here somewhere. So it is actually totally theoretical that our second point could be back here and still be called A plus h. H could be negative. All right, so what is this second point now? The point that we were calling Q, we can actually give it some coordinates now. Its x coordinate is A plus h, and its y coordinate would be f of A plus h. Once again, find the slope of the secant line, the black line here that connects these 2 points. M secant would equal the y coordinate minus the other y coordinate, so f of A plus h minus f of A, and then all of that divided by the difference in the x coordinates, A plus h minus A. That's really no different than f of B minus f of A over B minus A, just with the substitution that B is now called A plus h. But however, this can be simplified so that the denominator, the a's cancel, and we just have h in the denominator. Again, this is still just the slope of that black line. But before, when we said that we wanted Q to approach P, what we really meant there was that we just need to have the horizontal distance be smaller. And then in this case, that would be the magnitude of h we want to be smaller. And that's when we start saying we want h to approach 0. And remember, h can be positive or negative. But if you look at this formula, h is not allowed to equal 0 because that's not in the denominator of this rational expression. And therein lies the big problem. We want to get closer to 0, but we can't let h equal to 0. This turns a problem where, most of the time in algebra, we plug in a value and we evaluate it. Now we have a conceptual idea. We want h to get closer to some goal, and we can't actually let it equal that value. So it's not just a matter of substitution. And that's where we invented calculus. We need this concept that we call a limit. The idea here of limits is we would write something of the form LIM, short for limit, and below that we would say we want h to approach 0. And then after that would be some sort of expression involving h, and in that expression we want to see how close we get to 0 affects the overall valuation of that expression. So limit as h approaches 0 means get close to 0 but without equaling it. And now we see that this becomes the problem to solve here. Slope of the tangent line is the slope formula of the secant line, but taking the limit as h approaches 0. Now, this piece in here, the slope of the secant line, you could just call it the slope of the secant line, or if you want to be a little more formal, we tend to call this the difference quotient because, well, you're taking the difference of two y values and you're putting that into a quotient. It's not really that creative of a term. And we may have seen this already when we were just looking at function notation. And that would have been hopefully seeing something of that form that we can simplify. And then we take that And now we're going to apply the concept of limits to it, which is what we're going to be looking at in quite a few videos now coming up, is how do we evaluate limits of these expressions when you're trying to conceptually let a variable get close to a value without substituting it in. Well, I hope that gives you a little bit of an idea about why suddenly we need calculus. We're going to look at how to actually calculate limits, but now you have an idea about what our goal is, and for the next few videos we can take a look at limits and come back to this so that we can evaluate these kinds of expressions and limits. Thanks for watching, and I guess I'll see you in the next video.